Hello! We're going to start talking about projectile motion. And we're going to start off with problems that I like to call kicked, flicked, and pushed. You'll see why in a second. By now, you're quite familiar with analyzing motion on one axis, motion in one dimension, whether it's on the x-axis or the y-axis. And you're familiar with using the kinematic equations to do so. That'd be these four, sometimes called the golden equations. By now, you're also familiar with taking vectors and resolving them into their components. Well, these are all the skills that you need to analyze motion on two dimensions. So, when motion is occurring in two dimensions, analyzing it using the kinematic equations on its face seems crazy. But if you take the motion and resolve it into the components of the motion on each axis, you can then apply the equations for one-dimensional motion to the motion occurring on each axis. The components are analyzed independently, but put together. It sounds tougher than it is. You'll see. So we'll start talking about projectile motion, as I said, with what I like to call kicked, flicked, and pushed problems. And while any object launched into the air is a projectile, as long as it's only falling under the influence of gravity, projectile motion is just free fall with some initial velocity. And the first kind of problems we're going to talk about are free fall where all of the initial velocity is on the x-axis. We ignore air resistance to make things easier on ourselves, and that makes the path of any projectile a parabola. If you're going on in physics or into engineering, you will not get to ignore air resistance forever, but at the level of high school physics and even early college physics, for classic Newtonian motion, we tend to ignore air resistance. Okay, so let's look at two balls falling. The red ball is falling straight down. It's a standard free fall problem like you've done, while the yellow ball has some initial velocity on the x-axis. It's important to note that neither ball has an initial vertical velocity. In other words, the VIY is equal to 0 meters per second in both cases. Their vertical motion is just free fall with an acceleration of negative 9.81 meters per second squared. And in fact, if you look at the position of each ball at each point in motion, they're even, they're lined up. Because no matter what the initial horizontal velocity on the yellow ball, its vertical motion is still purely free fall. To analyze that, all we need are our four golden equations. So we said that the red ball has no horizontal velocity, and we just treat it as a simple free fall problem. Even though the yellow ball has an initial horizontal velocity, it doesn't have any acceleration on the x-axis. So its velocity on the x-axis is fixed, it's constant. Therefore, Vix equals Vfx equals just plain old Vx. The acceleration on the x-axis is 0. A sub x equals 0. That means when we're looking at a horizontally launched projectile, we can say V sub x is equal to delta x over delta t. That's going to come in really handy. Okay, with that, let's get to work on sample problem 3D on page 101 of your Holt Modern Physics. In this problem, we're told that the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a little rock horizontally off the bridge. The rock hits the water with such that the magnitude of its horizontal displacement is 45 meters. Find the speed at which the rock was kicked. All right. For these kind of problems, we're going to do something that's a little bit new. We're going to list our variables for the x-axis and the y-axis separately. You'll see why in a little bit. So on the x-axis, we have some Vix. And since we know that that's the total initial velocity, we can just call that Vx. We know that acceleration on the x-axis is equal to 0. And we know that there's a delta x of 45.0 meters. Okay, we'll stop there for the moment. On the y-axis, we know that VIY was equal to 0. We know that the delta y is equal to negative 321 meters. And we know that acceleration on the y-axis is the only acceleration we have, and that's good old negative 9.81 meters per second squared. Now, I very intentionally left delta t for the end. In these kind of problems, time often forms the bridge between the two axes, because for every moment in time, there is some position on the x-axis and some position on the y-axis. Since the velocity on the x-axis is constant, we're going to build an expression for time that references variables that we either have or are looking for. Remember that we said that on the x-axis in these types of problems, since velocity is constant, we can put this into old simple terms of v sub x equals delta x over delta t. We're going to use that and rearrange to solve for delta t. So that would give us delta x over v sub x. Okay. For now, we'll just kind of leave time on the y-axis alone. Remember, this is what we're interested in, v sub x. Okay, now if we were just looking at what we have on the y-axis, and we had these four things to work with, VIY, delta y, AY, and delta t, it would be a pretty easy bet that we were going to use delta y equals VI delta t plus 1/2 a delta t squared. This is especially easy considering that that's going to go away because VIY is equal to 0. So let's go ahead and make some room so we can start working this problem in earnest. It's important to note that at this moment, everything that we have in this problem represents something on the y-axis. So we have delta y, this was VIY, which is why we were able to cancel that. This is acceleration on the y-axis, and of course delta t is shared. So bringing this down, we have delta y equals 1/2 a delta t squared. How will we connect this back to the x-axis? Aha! With that. So let's substitute. We now have delta y equals 1/2 acceleration on the y times the quantity delta x over v sub x squared. Good. We now have an expression that's made up of all either things we have or things we want to find. We have delta y, we have acceleration on the y, we have delta x, and we're interested in finding delta v sub x. So let's do some algebra. First of all, remember that squaring the quantity of delta x over v sub x is the same as squaring delta x, as having quantity delta x squared over v sub x squared. That's going to become important to our rearrangement. Now, let's begin the process of isolating this. We'll start by moving our 1/2 on our acceleration on the y-axis over, which gives us 2 delta y over ay equals delta x squared over vx squared. We're now in a position where it's not too terribly difficult to rearrange. If we first get this out of the denominator by doing this, 2 delta y times v sub x squared over a sub y is equal to delta x squared, we're now in a position where we can fairly easily rationalize this and then isolate v sub x by dividing both sides by 2 delta y. Now, taking the square root of this side eliminates the vx squared, and we're done. Now it's time to plug stuff in. This gives us v sub x is equal to the square root of 45 meters squared times negative 9.81 meters per second squared divided by 2 times negative 321 meters squared. This gives us a value for v sub x of 5.562621,415 meters per second. With sig figs, of which we have 3, this would be a VI of 5.56 meters per second. Okay, not so bad. You'll get plenty more practice as you start on the 3D practice problems, numbers 1 through 4. Okay, get going.